Let me see if I can do any more cleaning up here. How about we square this square root? What would happen if I square that square root? Goes away, and then the negative distributes. So you get negative x squared, and then plus 1, and then you had a 1 out here. So plus 2. Yes? And then on top, anything left on top? That x out there? So we should have the x way out here, from out here, over square root of 2 minus x squared. That's this right here. And then we still had this one right here, square root of x squared minus 1. And you could go even further and put these two together. Since they're both square roots, you could take the insides of them and multiply them together. But I'll just say that's good enough. Any questions? All right, now I just told you again that the formulas for these are in the book and on your formula sheets, but there's one in there that I'm just going to jot down on the side here, because this one's going to come up a lot for us. The derivative of arctangent of x is 1 over 1 plus x squared. The derivative of arctangent of x is 1 over 1 plus x squared. Put a big star next to that, because that will follow us for the rest of this semester. That one comes up. So I'm doing example 4 now. If y is equal to the square root of the natural log of arctan of x, I want us to find y prime. I'm going to let you try that for a few minutes. See how you do with that. See if you can find that derivative. Go ahead. Sorry, you're okay. Wow, this thing is really having trouble focusing. Y'all can talk to each other. That's okay. See if you can get it. I'll be right back. I'm going to try and grab some black markers.
So 1 over
going to start writing the solution up here. All right, that's the uncleaned up version of the answer. There's not a whole lot you could do to clean this up either, because you just multiply all those together and just leave them down there. So let's talk about this. What is the derivative of the square root of something? 1 over 2 times the square root of that something. Then you're done with square root. Okay, what's the derivative of natural log of something? 1 over that something, right? Done with the natural log. What's the derivative of arctan of something? 1, or arctan of x? 1 over 1 plus x squared. And you're done. That's it. Okay, let's do the next example. Example 5. So for example 5, you'll notice that this equation cannot easily be solved for y. And we ran into this in Cal 1. We ran into equations that cannot explicitly be solved for y, and in that case we could not find the derivative explicitly, we found it implicitly. So we just want to do implicit differentiation on this. So the derivative of the left side, what is the derivative of arc sine of something? 1 over the root of 1 minus the something that we have, which in this case is xy squared, but then squared. So that's the derivative of arc sine of this junk right here, right there. But then chain rule says we now need to take the derivative of what's in here. And that's going to require we do a product rule, isn't it? So I have times, here comes my product rule. And my product I'm talking about is the product that occurs between the x and the y. So what's the derivative of x? 1 times y squared plus, product rule, derivative of y squared. 2y, I heard it, y prime, then times x. So applying the product rule to this expression results in 1y squared plus 2y y prime times x. Hopefully that rings a bell again from Cal 1, the implicit differentiation on that. You have to be very careful with that y prime, right? If that doesn't pop out, you're doing something wrong, and you never have y prime in here, and then you can't ever solve for it. Does that take care of the left side? Yes. So equals on the right side, what do we do? Term by term, right? Derivative of 1, 0. Here, another product rule. So what is the derivative of x? So it's the same thing as the left side, except instead of y squared, I've got y. So it'll be y plus y prime x. Now what we would need to do, that I'm not going to do, is we would actually need to free y prime. We would need to free it from the parentheses, which means we'd have to distribute this ugly thing through to the two terms here, which would just be, what, the first term? I'll just write the first one down. It'd be y squared on top of that. Right? And then the next one would be all of this junk on top of that. And then equals the other side. And then what you do is you get all your y primes to one side, everything that doesn't have y prime to the other, and factor y prime out, and divide through. So if you need to go back and review implicit differentiation from Cal 1, go ahead and do that. Because if you go back and review, you'll realize that solving for y prime was always kind of not the harder part of the problem, but the more tedious part of the problem was getting the y prime alone. Any questions? What are we doing on time? Got about 30 minutes? Okay. I need to be quick here. We're going to example 6. Example 6, 3.5. A rocket is fired straight up with a speed of 1,000 miles per hour. An observer who is a mile away from the launch point is tracking the rocket with binoculars. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? What is that in degrees per second? Okay. So I'm going to draw a picture, because that's the way we do related rate problems. That's what this is. So I'm going to draw a picture. I'll put my rocket right here. So here's the launch pad. My rocket is going to be fired straight up like this along that line. My observer is on the ground, I'm assuming, perpendicular to that launch point. And the rocket is moving along that vertical line. Yes? So my rocket is at some point like this, moving this direction at 1,000 miles per hour. Agreed? That red point's moving. My observer is how far away from the launch pad? What is it? An observer who is a mile away, so 1 mile, is watching this thing go up, right? So depending on how you were taught related rates, what I say may kind of sound like new to you. I always told my students with related rates to do what? 2 different pictures, right? One picture of what's happening in general, and another picture of what's happening exactly at the moment we're talking about. So I'm going to let this one over here be my general picture. And then another picture over here is going to be the exact moment in time. With my moment in time picture, what changes is that I can fix the rocket, can't I? I can fix the rocket to be how high? 3 miles. Which creates a right triangle. So now what? I guess I'll draw a line connecting. I'll make it dotted, connecting my observer. We want to know how fast is the observer's angle of inclination changing. That's this angle right here. We want to know how fast that's changing. Agreed? Let's call it theta. So we actually want, what is it that we want to find? How fast is the observer's angle of inclination changing? So we don't want theta, we want d theta dt. We want to know how quickly the angle is changing with respect to time. Right? It's one thing to figure out what theta is, right? If I give you a triangle that's fixed, right, like this, can you tell me what theta is? Could you actually find that angle? Yes, because it's fixed. But we know that the rocket has never stopped. We're trying to find at an instant how fast that's changing. So we don't want to know a static moment in time. We want to know how things are related to each other as they change. So we want this. When do we want this? When the rocket's 3 miles high, right? So what we need to do is come over here to this picture, and we need to label the distance between the rocket and the ground as a variable, because it's changing throughout the problem, isn't it? So why don't we call it h for height? The height of the rocket? Over here, at the moment in time, h is 3, isn't it? So what I could say is that I would like to know how fast the angle's changing when exactly at the moment that h is 3. Does that make sense? Now, it's also wise to write down the information that you're given. What is it that you're given in terms of a rate? Are you given a rate here, a derivative? Anyone? The speed of the rocket. The speed of the rocket. The speed of the rocket is telling you how fast h is changing with respect to time. So it's dh dt, isn't it? So we're given that the change in h with respect to time is 1,000. And I believe that's all of the information that I really need to actually do the problem. So does anyone remember what the next step is once you've kind of written down, drawn your pictures, written down the things that you want to find, the things that you're given? Find an equation, connecting. I like to always say try and connect that variable and that variable together. Connect theta to h. If you can connect theta to h, you're done. You have an equation. So you can't look at that picture, you have to look at this one. What equation relates theta and h together? Tangent. Tangent. Because now you could say sine, couldn't you, or cosine? Well, sine, not cosine. Cosine has this and this, and that doesn't have h. But sine you could say, right? But you don't know what the hypotenuse is. You know this side. It never changes. So using tangent will make sure that that doesn't ever change. So the equation that I'm going to use, I'm out of room. The equation that I'm going to use for this problem is that tangent of theta is equal to what? H over 1? H over 1? Okay. H over 1. Now, how would you do this in Cal 1? At this point, once you have this, what would you do? Derivative on both sides with respect to time, right? That's the way you do it. So up to this point, like what's new? I haven't shown you anything new, have I? There's nothing new. But this section is about what? Inverse trig functions, right? So check this out. What is it that we want to know? D theta dt. Wouldn't it be nice if we had theta by itself? Yes? So before I take a derivative here, let me just get theta by itself by doing what on both sides? Arctangent on both sides. So if I take the arctangent of the left side and I take the arctangent of the right side, what comes out of the left side? Theta within the domain restrictions that you can read about in the book. I'm not going to stress that too much. Theta would be this. And the right-hand side is arctangent of h. So there's good news and bad news here. The good news is that if I take the derivative on both sides with respect to time, what's the derivative of theta with respect to time? D theta dt, and that's exactly what I want, and I'll have it solved for already, won't I? The bad news is that I need to be able to find the derivative of an arctangent. But that's what we did today, right? We know the derivative of arctangent is right here. Yes? So the point is that if you didn't look at this stuff in Cal 1, you would have taken your derivative here. And it would have taken you some time to get d theta dt by itself, and you'd have to work out a lot of stuff. Let me finish and I'll show you. But with today, we take the derivative. I always use a squiggly line to let people know I'm taking the derivative with respect to time. D theta dt. Anybody from another class ever have a way of representing the fact that they're taking the derivative? Like any notation? No? Just a d on the outside? Yeah. I just want everyone to know that I went from here to here, I took the derivative implicitly. So I use a squiggly line to let everyone know I did that. All right, so the derivative of the left side is that. What's the derivative of the right side? And be a little careful with this. 1 over 1 plus h squared. Good. Times dh dt. Times dh dt. Chain rule, right? The derivative of arctangent of something is 1 over 1 plus the h squared, but then you always have to take derivative of what's inside, and because it's with respect to time, The derivative of h with respect to time is dh dt, so it pops out. Got it? Now, can we solve this right now, straight away? Do you know what h is?
Yes.
3. Do you know what dh dt is? Yeah. We're done, right? I mean, that would be pretty easy to plug in. Now, let me contrast that with, well, let's actually get the answer and then I'll come back. 1 over, what's this going to be? 10 times 1,000. Why did I put plus? No idea. 1,000. Which is 100 d theta dt is 100 what, though? Radians per second, degrees per second. So let's see if anyone can remember this. What is time measured in this problem? This 1,000 was 1,000 miles per hour, right? Miles per hour. So our time increment is hours. What is our theta increment? What is our theta measurement? It's an angle, right? Radians always. You convert to degrees later if you want, but your answer is going to be in radians. So this is 100 rads per hour. 100 radians per hour. If you say 100 degrees per hour, it's incorrect. Now, what was the second part of the problem that I told you I wanted to know? What is that in degrees per second? Because I wanted to make sure you knew how to convert that to degrees per second. Because if I tell you, look, there's an angle, it's changing 90 degrees per second, then I think everyone understands like 90 degrees is this, 1 second is about that. So you kind of have an idea of what 90 degrees per second is, right? But 100 radians an hour, do you have any idea how fast that is? Not really. So let's convert it to degrees per second. So how do we convert this? 100 rads over 1 hour. So this is, we call this dimensional analysis. All you're doing is changing units. So let's go for the hours first. How can we get hours to seconds?
3,600.
3,600 seconds in 1 hour. So we put 1 hour up here. We put 3,600 seconds down here. Good. And then how do we get to, right, our hours will cancel, and so we'll have seconds on the bottom. How do we get to from radians to degrees? 180 degrees is pi over 2, or sorry, pi radians. Pi rads, isn't it? A pi is 180 degrees. So anytime we want to go from radians to degrees, we multiply by. So I'm going to put rads here, and I'll put degrees up here. So that way the rads will cancel. And then I use that conversion. Pi down here, 180 up here. Do you agree? Pi radians is 180 degrees. The rads cancel. And so let's multiply that. Someone on their calculator, take 100 times 180, divide by 3,600, and then divide again by pi. Let's see what someone gets. Anyone? Approximately 1.59 degrees per second. Anyone else get 1.59? Yes? Okay. 2 people got it. We'll say that's good. 1.59 degrees per second. You kind of have an idea of what that is, you know, like 1 degree a second. It's not too fast, is it? All right, whatever. That was only the speed at that instant. An instant later, it's a different speed, a different rate that it's rotating. All right, there's a homework assignment at the back of this on the bottom, homework, all right, which I do want you to do, but there's some other stuff I want to do. I still have you for 14 minutes. This is, was that it? Yeah, that was where I said we hadn't done anything new, right? And then what I did was I took arctan on both sides, and then it came out super clean, didn't it? But in Cal 1, what we would have had to have done is we would have taken the derivative here. We would have had derivative of tangent theta, which is derivative secant squared theta, then chain rule d theta dt, so there's our d theta dt, and then the right side would have been dh dt. And see, the challenge here is that, yes, you can get d theta dt. Yes, you know dh dt, but what are you going to need in order to figure this out? You're going to need to know what theta is. So then you have to go back to that general picture, or not the moment in time, and you have to actually figure out what theta is. And then figure out what secant of that is, and then to square it. And it's just a little more work, where doing the arctan on both sides right away, we didn't need any information about theta itself. All we needed was h and the speed. We were done. What's that saying? There's more than one way to skin a cat, I guess. I've never understood that, but you know the saying? That's kind of the same thing. And there's a more efficient way to do that problem, and it's the way we did it. So what I'm going to do now is, like I said, I'm doing this as an internet class also, and they have homework that's based on the book. And so for the next 15 minutes, 12 minutes, whatever it is, I'm going to do some problems that I think are good, that are related to the homework. You'll see problems like this too. It's not your homework problem exactly, problem for problem, but it'll give you some idea of what to expect. And hopefully what you'll see with this is that it can get a little more complicated than what I showed you in class. Here's one. I'm going to put number 2 only because, again, my internet students, when they do their homework, that's going to be number 2 for them, but that doesn't relate to you. All right, so they're given this arctan square root 1 minus x over 1 plus x, and they're asked to find y prime. So this is just chain rule. That's all this is. So let's see how this works out. What is the derivative of arctangent of something? Uh-oh. One over 1 plus whatever was in it squared. Well, that's nice, isn't it? Because it's going to square that square root. Times now chain rule. We have to take derivative of what was inside the arctangent, which is a square root, right? And the derivative of the square root of something is 1 over 2 times the square root of that something, which in this case is 1 minus x over 1 plus x. So that's the derivative of the square root of this junk right here. And then continuing chain rule, I have times the derivative of what's inside of the square root. And what am I going to need in order to do that? Quotient rule. And I'm not going to work through it. You can do quotient rule on the side, do your f prime g minus g prime f all over g squared, figure all that out, and clean it up. You should get negative 2 over 1 plus x quantity squared. So lots of good things happen. Things cancel with the quotient rule. You just get a negative 2 up there. So the reason I'm showing this to you is because this cleans up quite a bit. And I want to make sure everyone's comfortable on the cleanup for this. So I'm going to first start by putting these two together. So how do I put those two together? Turn that 1 into 1 plus x over 1 plus x. get a common denominator, and smash these together. I'm going to do that without showing the work. Again, I just want you to know what I'm doing, putting these two terms together. That'll leave me with a 1 over, and when you do that, you get, it really cleans up nice, 2 over 1 plus x. On this next term over here, or these next two factors, I should say, do you agree that that 2 and that 2 would cancel, but you still have a negative 1 up there? Okay. On this one, do you agree that the square root of a fraction is the same as a square? You could do the square root on top and bottom separately, right? I could break this into 2 square roots, like square root up here, square root down here. And then you have 1 over a fraction, which is the same as the reciprocal. So this whole thing's just going to flip, and it's going to turn into this. Square root 1 plus x over square root 1 minus x. And then this one out here times, there was a negative 1 up top still, 1 plus x quantity squared. Anybody see anything? Wait, hold on a second. Yeah, no. Yes, you can, but look at this right here. You were talking about this one? Yeah, just flip this one up. I thought I did that already. Okay, these two come together, I have this, right? On my next step, I can just flip this up. So instead of writing it all out, because I only have about 8 more minutes, I'm just going to do the 1 plus x up here over the 2, like that. And then notice that one factor here cancels with one of the factors here. So we get, okay, what's still on top? Negative square root of 1 plus x over, on the bottom, I still had a 2 down here. I had square root of 1 minus x, and then what's still down there next to that? 1 plus x, right? Is there anything else I can do? It'll go a little bit further. Yeah, this right here and this right here, if you look at this square root as really being raised to what power? 1/2. Then this is like x to the 1/2 over x to the first power, and you could subtract, 1/2 minus 1, and right, and you could simplify that. So when I simplify that, I get a negative 1 on top. The 2's still out there. 1 minus x is there. When I do these two together, 1/2 minus 1 is what? Negative 1/2. And so it should be 1 plus x to the negative 1/2, but then we drop it back down. And so it'll be 1 plus x to the 1/2 on the bottom instead. This is just algebra. I understand I still do see some looks of concern on your faces, but it is algebra, and I just want you to make sure you go and try and make sure you can do this, okay? And one last step. These two roots can come together because they're both square roots and it's multiplication. And that means I just multiply these two inner pieces together, don't I? And what happens when you take 1 minus x and multiply it times 1 plus x? You get 1 minus x squared. You get difference of squares. So your final cleaned up answer would be this. Right there. So the purpose of that problem was just to show you you got to be able to do the algebra in here. So there can be quite a bit sometimes. Okay, something else. How am I doing? Still got 4 minutes. How about this one? May I erase? Still getting this? Everyone done? Okay, next one. This is going to be it's going to seem completely unconnected to this. This is their problem number 6. Something like this. what is tangent of secant inverse of 5? So what I'll do is I'm going to call this piece right here U. This has to do with reference triangles, all right? That's the way you can attack something like this. I'm going to call that piece U. Is everyone okay with that if I call that U? All right, so I'm going to write that down. U is equal to secant inverse of 5. Now what I'll do is I'll take secant on both sides. Secant U is 5. Can somebody help me draw a triangle that represents that equation? A right triangle. What's my angle? What do I call the angle? Theta, x, y, z, what? U. Because U is this, right? Secant of an angle is 5. And 5 has to be the what side over what side? Secant is, this is hypotenuse over adjacent. Secant's the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So this is 5, and this is 1 right there. Now, the reason why I want that is because what is this question really asking me? What is tangent of U? Here's your picture. Tangent is this, right? So you just need to find that side, which again, you could do Pythagorean. If you do Pythagorean, it's actually this, square root of 24. So what's the answer to this? What is tangent of secant inverse 5? Well, that's the same as saying what's the tangent of U. And according to my picture, tangent of U is this side over this side. So root 24, and then you could simplify that, but I'm just going to put, what would it be, 2 root 6? 2 root 6. Root 24 is 2 root 6. God, I'm out of time. I tell you what, you're free to go. I'm going to do a couple more problems. You're not going to hurt my feelings. You go. But I wanted to do a couple more problems more for my internet students. So I will see you all next time if you want to go. I'm only going to probably go for like 10 minutes. Do the homework that was on the end of those notes. Do those problems. Make sure you do the online quiz where you say you've watched the orientation, you know what's going on in the class. Print out the notes for next section, because the next time we're covering what? 3.6 hyperbolic functions. Okay, so print out those notes. What else? I think that's it. Yeah, that's it. Really, don't feel committed to stay. I mean, I don't want you to feel like I'm going to call you out or anything. I will normally take attendance. I didn't today. But I'll normally pass this around, and it'll have a place where you initial. Start doing that next class. All right? This problem is tricky because you have a 2 in here. So the key to this problem is to recognize a formula from pre-cal, which was something like sine of 2x equals 2 sine, well, usually they use theta. Is 2 sine theta cosine theta. It's a double angle formula from pre-cal. And so if I look at it that way, this piece is like the theta. And so I will call it U again, so that this thing really looks like sine of 2u. And according to that formula, this is 2 sine u cosine u. So I just need to figure out what sine of u is and what cosine of u is. And then I'd be done. So over here on the side, I'm going to create my reference triangle. What was u? I'm not asking y'all questions because I'm assuming y'all aren't here anymore. Okay. What is u? U is cosine inverse of 3/5. take cosine on both sides. Cosine u is, everything goes away here, 3/5. Triangle u, cosine is adjacent over hypotenuse. So adjacent over hypotenuse. And we should be able to get everything else from that. This will be a 4. If you solve for it, this will be 4. And so when I come back over here and I say I needed to know what sine of u was, sine of u is 4/5, right? Opposite over hypotenuse. Cosine of u is adjacent over hypotenuse. I actually knew that already, but it's there in the triangle also. So this is 2 times 4/5 times 3/5. Multiply across, you're done. So what, 8, 20, what is that, 24 25ths. So sine of 2 cosine inverse of 3/5 is 24/5. Okay, I have time for one more, and it's pretty ugly. It's pretty ugly. Let me see. Hey, where are you going? I'm just kidding. All right, y is equal to, the algebra of this problem is pretty nasty. All right, so find y prime. So we have an arctangent, and inside of that we've got some stuff going on. And we have a 7 in front of everything. So the 7's just going to follow along for the ride. 7 times the derivative of arctangent of something is 1 over 1 plus that something, which is x minus root 1 plus x squared, but that whole thing squared. That's the derivative of the arctangent part. Now you have to multiply times the derivative of what's inside. And since there are 2 terms, I'll do them one by one. So the derivative of x is 1 minus, now I take the derivative of the square root of something, which is 1 over 2 roots of that something. But then it's the derivative of what's inside of it, which is 2x, which I think, yeah, I'll just throw it over here. Like that. Whew, okay. These 2's cancel. That would be correct as an answer. I mean, as far as the derivative, that is correct. But the answer, if I'm not mistaken, that the computer wants you to put in, shoot, I didn't finish doing it because I saw how it was going to work out and I just stopped. So, but the answer that the computer wants is really, really clean. So let's check this out. What we're going to do first is take this right here, and I'll rewrite it x over square root of 1 plus x squared, like that. Over here, 1 over 1 plus, I'm going to square this, which means it's 2 terms, which means I have to FOIL this out. And that's going to be this term squared. Since there's a negative, it'll be this times this, and there will be 2 of them. So minus 2x root 1 plus x squared. Hope you understand I'm taking this times itself next to each other, and then I'm FOILing. Then the last term, which is negative root times negative root again, which is plus, the roots will square and go away and become 1 plus x squared. That makes sense? I'll ask you since y'all are here. Did that make sense, what I did? Okay. It's right there. I don't know what you're talking about. I must have been blocking it when I was standing there. You couldn't see it. Okay, so 7's there. So now I'll write down, let's see, does any of that clean up in here? The x squared and x squared is 2x squared. 1 and 1 is 2. And I have a 7 on top. So this is equal to a 7 on top. I have 2 plus 2x squared minus 2x root 1 plus x squared. That's just this part right here. It doesn't look like it's getting any cleaner. These two I'm going to put together with a common denominator. Okay? It's not ringing a bell. Yeah. These two I'm going to put together with a common denominator. So that means I have to turn this 1 into a root 1 plus x squared over another root 1 plus x squared. And then I can put them together. And so what I get out here is times square root of 1 plus x squared minus x, that's the numerator, this minus this, over the common denominator, which is square root of 1 plus x squared. We're getting close, but we're not there. The next thing I'm going to do is, since there's one term here and 1, 2, 3 terms here, I'm going to multiply this term through to each of these. And then on top, the 7 is just going to go up here. I'm just going to put a 7 and then that in parentheses. So here's where I am. On the top, 7 parentheses square root 1 plus x squared minus x. On the bottom, distributing this to the 2 gives me 2 of those roots. Distributing this to the 2x squared gives me 2x squared times the root. And then distributing this to this is where good things happen. You get the root and the root are exactly the same, so it goes away, and I'm left with, in parentheses, 1 plus x squared. I know this still looks bad, but it's actually about to get real nice. So all I did on this step was distribute a negative 2x through right there, like that. All right. Now something you can do here, it's not super obvious though. That's why I'm showing this problem, because it wasn't obvious. Is I'm going to take this term and this term, and I'm going to factor a 2 out of both. If I factor a 2 out of both of those, remember what we have on top. Don't forget about this. But if I factor a 2 out of both of those, what's left? Just the blue ones. 2, and then what's left there? The root, 1 plus x squared, and then what's left here? Minus x, parentheses. Do you see that that's the same as what we have up there? But we still have these two to work with, so we have to look at this one. Oh, wait, this whole thing and this whole thing. And what can I factor out of both of those? A 2x squared. So I pull a 2x squared out of those, and you're left with the root again, and then over here minus x. And since they all contain the same thing in parentheses, I can cancel it. Here, here, and here. They all had to contain it, though. That's why I had to wait that long to cancel. And so the final result is a 7 over 2 plus 2x squared. Or if you'd like, 7 over 2 times 1 plus x squared. I believe that's the way the computer looked at it. I think the computer will take more simplified versions, but that's the one that's in my answer key on the computer. So a pretty cleaned up version. There's a lot of algebra going on in that problem, which is why I wanted to show it. All right. I'm going to kill this video.